Hey everybody, thanks for joining us at Dash, and I hope you enjoy a lot of the talks going on today. Thank you for coming to my talk, Avoiding the Architectural Cascade. Today I'm going to be talking about some interesting architectural challenges that we faced at Zapier, and a lot of solutions going forward that can kind of help you avoid cascading failures as a result of those solutions and choices. My name's James Carr. I'm an early Zapier employee. I was actually our first engineering hire, and so during the early stages, I did a lot of different work and wore a lot of different hats. Product development, front-end development, and then over time, I got really excited about infrastructure and doing infrastructure as code. So I kind of started focusing on DevOps type work full-time and bootstrapped our SRE team at Zapier. And kind of fast forward to today, the SRE team is currently 7 people, spread out across 6 time zones and 5 different countries. We basically hired, and this will play into the story later, but we hired across different time zones to make it really easy to respond to on-call, because I hated getting on call at 3 a.m. or 1 a.m. or those crazy hours, right? So by hiring across different time zones, it was really easy to have people only be on call during their working hours. And so I'll play a bit to our story later. But basically, before we begin, I kind of want to give a quick outline of this talk and kind of what the content that I'm going to be covering today. So first off, there's going to be a few ground terms. Basically, I'm going to be talking a lot about some of Zapier's backend as part of this story. And so I'm going to define a few terms around, Zapier's domain logic, so things make a lot more sense when I actually talk about them. It's also going to be a tale of architecture, basically some of the architectural choices that we made earlier at Zapier and how those impacted things going forward and caused an interesting tale of incidents, and basically what our number one recurring incident was almost until just this year. And also it's going to be a tale of having a customer that's going through a hypergrowth phase, because I think everybody has regular customers, but then eventually you're going to have a customer that's just going to completely overload your systems and cause a lot of interesting problems with the architectural choices that you make. And then kind of moving on from that, just kind of talk a little bit about the lessons we learned, and as well as architecting for the future. So first off, just kind of I want to give a clear definition of what Zapier is and what we do, in case you might not be aware of it. So Zapier basically allows people to connect different web applications and different APIs and integrate with them. So for example, say you have a new Facebook lead, that triggers a follow-up email to your mailbox, and then also send a notification on Slack to let your team know that you have a new lead on Facebook. When Mike, Wade, and Brian first approached me to join Zapier, it was a really appealing idea to me because I had just came off a 9-month project where we integrated a CRM with Salesforce. Basically, it was an in-house CRM at the current employer that I was at. And it was a 9-month project just to integrate that with Salesforce as part of migrating to Salesforce, because they're going to eventually get rid of that CRM. So it's really appealing to not have to do all that boilerplate work and be able to just focus on domain logic and business logic and have something else manage that, right? And so some of the terminology behind Zapier, a lot of the domain concepts that are going to be an important layer in this story, is a Zap. A Zap is basically a term for all the different apps that we have integrated on Zapier. So for example, a Zap will be, you have a new Facebook lead, it notifies our team on Slack. And then there's a trigger. A trigger is what actually triggers the Zap. And at Zapier, we basically have 2 different ways things can get triggered. One is you can have a webhook that kind of triggers the whole workflow. For example, Slack sends notifications instantly through webhooks. Or it could be a polling API. So say, for example, if you're integrating with Salesforce, there's a leads endpoint that'll return 25 leads, the most recent 25 leads. And so what happens on Zapier is we just pull that endpoint every so often, every 5 minutes or every 15 minutes, and trigger when we see something new. And then also there's an action, which is basically anything that happens as a response to that trigger. So in this case, I kind of highlight Slack as the action. We're notifying the team on Slack. And Zaps have multiple actions, so you can have one trigger and then as many actions after that. And then Also, we have apps. Apps are just basically applications that are on Zapier that you want to integrate with. Um, then tasks, and this is kind of where it kind of gets to what we're going to be talking a lot about, is when we actually execute that Zap. So the trigger and the action that gets performed, that's considered a task. And each individual action in a Zap can be a single task. And finally, the main character in this story, I guess you could say, is the antagonist, will be the task history. And task history is something we created at the very, very beginning because there's a very obvious need that customers wanted to be able to see a history of the tasks that they've executed, the kind of data that kind of moved between Zaps, as well as like whether or not it failed or succeeded. So task history is going to be the main thing I'm going to talk about. I'm going to kind of give a brief overview of the front end and then dig into the back end because it's going to be the main part of like where we end up having a lot of problems as Zapier. So the task history basically looks like this if you're on the website. It kind of like gives you a list of all of your Zaps. You can see the details about the number of tasks that have ran for that Zap in this month, number of issues, and issues being whether you have like a 500 error returned from an API or your authentication failed, things like that. It's a pretty like straightforward overview of the different Zaps that you have. And this is like when you drill into the details and look at an individual task, you'll see like a very specific one. Like here's mine, for example, for getting things done Zap that I have. Like every Thursday, it basically creates all of my recurring tasks in Trello for me to follow up on. And so you can see like a Thursday at 5 p.m., it triggers. And then down at the bottom, it sent one new card to Trello with like no label and just the card position board. And if I scroll down further, it'd show the details of like the data that was passed over to Trello, but I kind of took that out because I didn't want to share what my actual to-do items are. So the infrastructure behind the scenes. This is what it looked like in its initial inception around 2015. It's pretty straightforward, basically. On the front end, you have the web application. That's where customers interact. And it talks to Elasticsearch, and it's really just doing searches against Elasticsearch. So that's pretty straightforward. It doesn't do any writes or anything. It just does simple reads. However, on the back end, whenever task workers are processing tasks, they're indexing the request and response of each of those tasks into Elasticsearch. And the task workers themselves are basically just tons and tons of instances running on the back end. They're just subscribing to RabbitMQ and just processing tasks that are getting fed into it either from triggers or from other actions. So this is the initial setup, and it works pretty well for us. It's pretty simple. Like a task gets processed, it just writes the results to Elasticsearch. Then on the front end, customers can search and see those details about their Zaps. But like any good product, over time we continue to add new features, and as we add new features, the product started to evolve in interesting ways, especially because a lot of the different features are being created by different teams who might not interact with each other very often. And amongst those features, I think one of the more interesting and important ones was Task Replay. So Task Replay came into inception because, say for example, you integrate with Gmail, and Gmail goes down for 20 minutes. And during the duration of those 20 minutes, 30 tasks attempted to write to Gmail. So what's going to happen at that point is those tasks are going to fail, and now you have 30 failed tasks, basically. And so what Task Replay did is allow people to go through a task history and just click a button to replay it. Or they could just if they pay for the feature, it just automatically replay those failures. And the way that worked is we basically just set up a separate queue. It's called Replay Node. And basically what happens is when tasks are marked for replay, they just get queued up and then they get processed. And they get processed a lot slower than normal tasks. And the reason for that is because if there's a huge outage on another API, say for example you're integrating with Evernote has an hour-long outage, and then once they recover, you have 10,000 tasks that are going to write against Evernote. That'd be pretty tremendously bad if we just slammed like that against all of our backend systems instantly. Especially if you take that and multiply it by all the customers who use Evernote, that's a lot of tasks that are going to just slam a lot of backend services. So we queue them up, and then we also stagger them out a bit. So for example, if you're that customer had 10,000 tasks, and the service is healthy again, and it starts replaying it, it'll just start replaying batches at a time, like 500 now, 500 the next 10 minutes, 500 the next 20 minutes. So it's pretty useful, but it also got implemented in a very interesting way. And that is we track the state along with the index payloads at this point. So like whether or not the task succeeded, whether it failed, whether it's pending, meaning it's like going to be replayed eventually, or whether it's like halted, meaning it hit an issue. So what happens, it's interesting when you update documents in Elasticsearch, is that it turns out that's a pretty expensive operation because it doesn't just update the document in place. What it's doing is it's creating a new document, marking the old one for deletion, and then replacing it. And so if you multiply that by tens and thousands of tasks and then also like hundreds of thousands of customers, that's like a pretty expensive operation that can happen. So this led to some interesting problems for us at Zapier. Like I mentioned, it's the tasks write to task history synchronously within the actual execution path. So what that means is it's very, very sensitive to latencies. So for example, if Elasticsearch is responding like say 50 milliseconds, 100 milliseconds, and then suddenly it jumps up to like 5,000 millisecond response times, tasks are going to slow down. And this is actually what our actual task queue looks like. And it's called Node behind the scenes. But this is an example of a time when a cluster went yellow. We lost like 2 servers because like the hardware got faulty. They got terminated by the auto-scaling group. New instances joined. And the cluster was yellow until it recovered. And what this means for our customers is instead of their tasks executing every 5 minutes instantly or every 15 minutes, like during whatever their plan is, they're going to start seeing tasks that will suddenly execute at 30 seconds or at 40 seconds or at an hour. And so at that point, they're going to see a lot of delays. And sometimes it's not very noticeable, but if it's something that's instant, for example, say if they add a React sheet on Slack and it adds an item to Todoist, like that's typically instant from their point of view. And if they do that, then it doesn't show up. And it doesn't show up 10 minutes later and 20 minutes later. That can be like really frustrating. They're like, oh, what's going on? Is this broken? Like, it'll take them there'll be a lot of confusion on what's going on. And in this like specific example here is the cluster went yellow around 2:30, I think, around 2:10. And then at 8 o'clock is when the cluster finally went green again. And then at that point, the queue started like draining, everything reached normalcy again, everything was normal. So it was like really, really sensitive to like any of those faults like that. And this led to a lot of firefighting too. Like I mentioned earlier, we had customers with like huge volume of tasks, and also they would also have like a huge amount of replays or like bulk tasks as well. And so a lot of times I put a lot of pressure on the Elasticsearch cluster and cause nodes to just get terminated or like Java processes to get locked up. And to be honest, we were not experts at Elasticsearch. So when you launch Elasticsearch and it's just a simple 3-node cluster, it's pretty easy to manage. But once things grow to a 30-node or a 35-node cluster, things get a little challenging, especially when it comes to like how you're using it, how you're routing like data to different shards. And so there's a lot of incidents and firefighting, I'd say, in 2015, 2016, maybe 2017, that, we'd be up late at night and have the cluster yellow or red and just be like looking up different configuration settings and tweaking them and trying things out to like get things back to a proper working order. And the good news is like we implemented a lot of different strategies, first off, to like solve a lot of the problems we hit. Like I mentioned earlier, like sometimes a lot of incidents were caused by customers that would suddenly, out of the blue, they just blast us with 200,000 tasks. Say they just like spun up some kind of service, just sync like 100,000 records to Zapier and like hit a webhook and have that webhook go to Salesforce or something. And so it caused like a lot of pressure points, especially on Elasticsearch being very sensitive as it was. So we implemented some mass task staggering, which that means is we like set some ceilings and some thresholds that if anybody like blasts us with like a huge amount of tasks that triggers that threshold, we need to just divert those tasks to a separate queue and process that queue a little bit more slowly, which is kind of nice because that way it doesn't impact other customers. It's just that one customer, like, they just blast 100,000 tasks at us, and they're going to see those get processed over time versus instantly. And a lot of times for customers that do something like that, they kind of have an expectation it's probably not going to be instant. So if they blast us with 100,000 tasks and it takes an hour for them to process, they're not really going to notice that. For them, it's just like, oh, it's working. Like, they're coming through one after another. So it's kind of nice. It was a really nice feature. And saved us a lot of headaches. Basically just made things a lot more stable and caused a lot less instant disk pressures from happening. Flow control is important, so without a doubt. So finally we reached some stability, so that's kind of nice. I think we had a good, maybe a year and a half that things were pretty nice and smooth and working pretty well. So in 2019, we ended up having fires happening a lot more often. It just started happening with a lot of regular recurrence. First it was once a month, then it started being a couple every month, and then it started happening every week. So something was going really bad here. While the incidents themselves were not very stressful, there was some stress there because you'd be watching a yellow cluster and kind of waiting for it to get green again and also have tasks backing up, and it's just not an enjoyable situation. So after a while, we started doing some investigation because the incidents kept happening more and more, and it started to become very, very stressful and very, very challenging. Not to mention that every time task processing slowed down and Elasticsearch slowed down, that impacted all the customers. So customers would be writing in and be like, hey, how come my Zap's taking 50 minutes to trigger? And it used to be instant. All of a sudden it's taking ages to trigger. So we started investigating. And what we discovered is we had a customer that had taken suddenly a very significant growth. They had a very steady increase in tasks month over month. And basically what they were starting to hit is they were actually hitting, once this was happening on a weekly basis, they were processing easily about 20 million tasks per month, which is a pretty significant amount. And one thing we also noticed too is the same nodes kept failing due to disk or memory pressure. This quick kind of gave us the hint that there was a specific customer because the way we set up our shard routing is we routed based on customer ID. And so I actually reached out to Lindsay, our premium support, and said, hey, can you contact this customer and ask what are they doing? Because I don't want to just shut their Zaps off. That'd be terrible. We don't want to do that. But let's find out why they suddenly started having such a huge increase. And she chatted with them, and it turned out that they just redid a major component of their business to be driven completely by Zapier. And in addition to that, they just started expanding to multiple countries. At that point, they just been localized within one country, within 2 or 3 cities, and then suddenly they started expanding to multiple countries, then also into South America. So they were growing very rapidly. And we needed to solve it quickly because they were very happy with us. At the same time, they were starting to notice a lot of the slowdowns on their end as well. It was kind of interesting because in the beginning, when the incidents started happening, they weren't noticing the slowdowns, but then as time progressed, they started noticing them a lot more, and it started becoming a lot more urgent for us to solve it. So a few solutions we kind of came into. First off, on the Elasticsearch side, we added a few more configuration changes there to make things better. First off, more replicas so we could survive partitions a lot better. Also added better instance types, upgraded the most latest instance types that are available from AWS, because at the time we were still running a very, very ancient instance types, and they did not have very good performance. And like I said, we just continued to go through the Elasticsearch best practices and find the best settings to tune to make things better. This gave us some incremental improvements, but this was kind of the same as what we've been doing up until that point. It wasn't giving us any improved leverage though. Elasticsearch was still a very, very huge bottleneck for task processing because of the way that it was structured, the way it was being called. So we finally took some time out to make some overall architectural changes that evolved over time and are continuing evolving today. The first one was we took making the calls to Elasticsearch out of the execution path of the task workers. So at that point, instead of like just having our task workers calling Elasticsearch directly and being sensitive to its latencies, we just fired off a task to a Kafka or event to Kafka, and then had a task history indexer just pick up that event and index the payload into Elasticsearch. And then we hit some issues where payloads were a little too big to be pushed into Kafka, so we use S3 bucket in those situations as an intermediate stage, like put payloads into there if they're a certain size, then pull them down, and then process them through the task history indexer. This made things a lot better. This took all the calls to Elasticsearch out of the execution path. And so what this means is now when we're processing tasks and say Elasticsearch starts having latencies or it goes yellow, then it's no big deal. It's because tasks will keep processing at that point. They'll keep going. And for the customer's point of view, what they'll end up saying is they'll like go into Zapier and be in the Zapier app, and they'll see like a banner at the top of their task history that says task history like results are delayed, just meaning that the display of them is delayed. So it's really nice because that way they're still working, but it's just like one part of the site is just having a delay in process showing results. So this is where we're at today, and it's like a lot better already, but there's still some progress being made. There's like we can do like a lot better. So the next step is basically separating out the state storage as well, because while moving Elasticsearch out of the code path within the tasks solves a lot of problems, it's still pretty sensitive to a lot of the same issues, especially with updating the state, because the updating the state definitely puts a lot of pressure on Elasticsearch for like larger and larger tasks and payloads. So the next step is like, since we're already using Kafka, and we can just create a second service that consumes to the same event, and then that's the one that updates the state. So the task history indexer just indexes the payloads into Elasticsearch, while the task history state maintains the state and like updates that. And that can update that in PostgreSQL, but you can easily use any other data store. It's just more suited for that operation. It's just focusing on just updating like that one specific value instead of updating an entire maybe like 5 megabyte document. Still, there's still a little bit more room for improvement that I think we can do in the future as well. And that is by partitioning customers out a bit. And what this could be is like right now we're kind of multi-tenant. So if different components within this architecture slows down, then it's going to slow down for all customers, not just one. So the next phase is starting to partition customers out a bit more. So if there's like, say that one Elasticsearch cluster goes red, it'll just impact a subset of customers, not all customers. And so at that point, it's a lot better because instead of all customers getting task history delayed, for example, only like 5% or 10% of customers would actually see a delay in task history. So some lessons learned. I think it's really important to take a step back and look at the lessons that are kind of learned within this. Things that we apply now and also going forward, and things that I think that anybody could take away, regardless of what they're using behind the scenes, whether it's Elasticsearch, Kafka, Redis, RabbitMQ. There's like anything that you're using could have these same concepts apply. One is like define some really clear SLOs. I think one of the biggest problems for us is we always just like had alarms for things that were actually on fire. Like, you get the notification because the cluster just went yellow or red. And defining clear SLOs around latency and around saturation can really help in, determining when those SLOs get breached and having them be breached before they become an issue. So you can kind of like start getting ahead of when things are becoming more problematic and when they're going to be more problematic in the future. So I think that's really useful, and it's important to be able to utilize those SLOs as well as error budgets to be able to like schedule, okay, we need to take time out and re-architect a few things. Because that way you can re-architect with some safety, right? Instead of having to like architect under the gun, so to speak. Like, it's definitely not fun to have to try to like redo an entire architecture when things are on fire. So I think defining clear SLOs for like all of your subsystems can be really, really helpful. Also, consider the impact of multi-tenancy. Like I said earlier in the story, whenever we had queue backups because of Elasticsearch being slow or because a customer blasted us with, say, 5 million tasks, that'd slow things down for everybody. And it was a terrible situation because you can scale out the workers to process those tasks faster. And with our old architecture, it wouldn't help. But now it can help. It'll just task history will be delayed. But separating things out a bit and kind of going to a more like isolation, being able to have like less multi-tenancy and partitioning customers out within like their own isolated setups is really, really beneficial. And it's really nice to be able to have it so that customers with huge amount of tasks don't impact other customers. So build for isolation. I think that's probably the most important one. It's very, very easy to create systems that talk to each other point to point. Meaning, it's easy. Everybody knows how to launch a RESTful API, right? And it's very easy to just say, launch like 3 or 4 RESTful APIs and have those being called from, or whatever you're doing your main processing, whether it's the website or the tasks or backend processing tasks. And I think one thing that's important is like to move more towards isolating those systems out a bit so that their dependencies aren't as concrete. You're going to make it so that if one of those components fail, then it doesn't like bring an entire site outage or an entire processing outage. It just makes like a small minor impact to one thing. And it's one thing that gets really helpful when you start splitting things out to more microservices is failures, instead of cascading really hugely, once they're well isolated, they don't cause ginormous fires. They're just like, okay, this one service needs to get restarted, or this one service's database is having issues. Like fix that one database. So it's nice because it doesn't create a global outage. And then finally, events. Lots of events. And this really is just like an extension of isolation. Instead of doing point-to-point communication, it's a lot better to do asynchronous events as much as possible. In this re-architecture, when we move to Kafka, it's perfect because we actually build for the future now. We fire out that event. It's like a task got processed. Here's the state of it. And then we can create multiple consumers to do multiple things. And even right now, there's like 2 or 3 teams at Zapier that are working on additional products that are building off of those events. So it's really, really powerful because you can like expand your system and scale things out, offer new features, offer new products without having to deal with all of legacy code or having to deal with introducing more like bottlenecks or more like things that can like really damage throughput and performance. So that's my main takeaway. I want to thank you for your time and thank you for coming to my talk. If you want to chat with me, you can contact me at Gmail. I'm James at Zapier.com, or you can contact me on Twitter at JamesCarr. And then finally, please check out our website, Zapier.com/jobs. We're hiring SRE team specifically, so please join us if you're in the market. Other than that, thank you for coming. And next up, please get in touch for a Q&A. Thanks.